Could building telescopes on the moon be the future of astronomy? What was once a pipe dream is fast becoming a very technological possibility. Lunar exploration is undergoing a renaissance. Dozens of missions organized by multiple space agencies and increasingly by commercial companies are set to visit the moon by the end of this decade. Most of these will involve small robotic spacecraft, but NASA's ambitious Artemis program aims to return humans to the lunar surface by the middle of this decade. There are various reasons for all this activity, including geopolitical posturing and the search for lunar resources such as water ice at the lunar poles, which can be extracted and turned into hydrogen and oxygen propellant for rockets. However, science is also sure to be a major beneficiary. The moon still has much to tell us about the origin and evolution of our solar system. It also has scientific value as a platform for observational astronomy. The potential role for astronomy of Earth's natural satellite, the moon, was discussed at the Royal Society meeting earlier this year. The meeting itself had in part been sparked by the enhanced access to the lunar surface now in prospect. Far side benefits? Several types of astronomy would benefit. The most obvious is radio astronomy, which can be conducted from the side of the moon that's always facing away from the Earth, the far side or the dark side. The lunar far side is permanently shielded from the radio signals generated by humans on Earth. During the lunar night, it is also protected from the sun, and these characteristics make it probably the most radio quiet location in the whole solar system, as no other planet or moon has a side that permanently faces away from the Earth. It is therefore ideally suited for radio astronomy. Radio waves are a form of electromagnetic energy, as are, for example, infrared, ultraviolet, and visible light waves. They are definitely defined by having different wavelengths in the electromagnetic spectrum. Radio waves with wavelengths longer than 15 meters are blocked by Earth's ionosphere, but radio waves that are wavelengths much reach the moon surface unimpeded, and for astronomy this is the last unexplored region of the electromagnetic spectrum. It's best studied from the lunar far side. Observations of the cosmos at these wavelengths come under the umbrella of low-frequency radio astronomy. These wavelengths are uniquely able to probe the structure of Earth's universe, the early universe, especially the cosmic dark ages, an era before the first galaxies formed. At that time, most of the matter of the universe, excluding the mysteriously dark matter, was in the form of neutral hydrogen atoms. These emit and absorb radiation with a characteristic wavelength of 21 centimeters. Radio astronomers have been using this property to study hydrogen clouds in our own galaxy, the Milky Way, since the 1950s. Because the universe is constantly expanding, the 21 centimeter signal generated by hydrogen in the early universe has been shifted to much longer wavelengths, and as a result, hydrogen from the cosmic dark ages will appear to us with wavelengths greater than 10 meters. The lunar far side may be the only place where we can study this. The astronomer Jack Burns provided a good summary of the relevant space background at the recent Royal Society meeting, called for far side of the moon as pristine, quiet platform to conduct low radio frequency observations of the early universe dark ages, as well as space weather and magnetosphere associated with habitable exoplanets. Signals from other stars. As Burns says, another potential application of the far side radio astronomy is trying to detect radio waves from charged particles trapped by magnetic fields, magnetospheres of planets orbiting other stars. And this would help to assess how capable these exoplanets are of hosting life. Radio waves from exoplanet magnetospheres would probably have wavelengths greater than 100 meters, so they could require a radio-quiet environment in space. Again, the far side of the moon will be the best location. A similar argument could be made for attempts to detect signals from intelligent aliens, extraterrestrials of course, and by opening up an unexplored part of the radio spectrum, there is also the possibility of making serendipitous discoveries of new phenomena. We should get an indication of the potential of these observations when NASA's Lucy night missions lands on the lunar far side in 2025 or 26. Greater depths. The moon also offers opportunities for other types of astronomy as well. Astronomers have lots of experience with optical and infrared telescope operating in the free space, such as Hubble telescope and James Webb. However, the stability of the lunar surface may confer advantage for these types of instruments. Moreover, there are craters at the lunar poles that receive no sunlight. Telescopes that observe the universe at infrared wavelengths are very sensitive to heat and therefore have to operate at low temperatures. The James Webb telescope, for example, needs a huge sun shield to protect it from the sun's rays. On the moon, a natural crater rim could provide this shielding for free. The moon's low gravity may also enable the construction of much larger telescopes than is feasible for free-flying satellites. These considerations have led the astronomer Jean-Pierre Millard to suggest that the moon may be the future of infrared astronomy. The cold, stable environment of permanently shadowed craters may also have advantages for the next generation of instruments to detect gravitational waves, ripples in space caused by processes such as exploding stars and colliding black holes. Moreover, for billions of years, the moon has been bombarded by charged particles from the sun, solar wind, and galactic cosmic rays. The lunar surface may contain a rich record of these processes. Studying them could yield insights into the evolution of both the sun and the Milky Way. For all these reasons, astronomy stands to benefit from the current renaissance in lunar exploration. In particular, astronomy is linked to benefit from the infrastructure built up on the moon as lunar exploration proceeds, and this will include both transportation infrastructure, rockets, landers, and other vehicles to access the surface, as well as humans and robots on site to construct and maintain astronomical instruments. But there's also a tension here. Human activities on the lunar far side may create unwanted radio interference, and plans to extract water ice from shadowed craters may make it difficult for those same craters to be used for astronomy. And as my colleagues and I recently argued, we will need to ensure that lunar locations are uniquely valuable for astronomy, are protected in this new age of lunar exploration. This is by Ian Crawford, Professor of Planetary Science and Astronomy, Birkbeck University of London, Professor of UCLA, on the conversation. Creative Commons here on Unexplained Mysteries. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.